Thank you very much. Thanks first off to Jürgen and all of the organizers for the invitation. I'm really honored to be invited. It's been just a phenomenal week so far. Hopefully I can live up to the quality of the talks we've seen up till today. So I am on the faculty in Materials Science and Engineering at Carnegie Mellon. And if I have some time at the end, I'll actually talk about some work by my group that we've done in the last couple of years. But when I thought about the sort of theme of this workshop, it really seemed that some work that I'd done as a postdoc was a much better fit for the overall theme. So most of the work I'm going to talk about in this talk will actually be work that I did between 2019 and 2022 when I was a postdoc, also at Carnegie Mellon. And there have been two previous talks in particular that have set up this stuff really, really well. The first was Martin Bazant's talk yesterday. A lot of things in here are built fairly directly on things that he's established over the years. And he's actually cited pretty voluminously through here. And then the second, of course, is Michael's, because a lot of the numerical and computational stuff that I'll show was done in a package I built in Julia. And I think Julia users often follow the same joke about, like, how do you know someone's a vegan? They'll tell you within like 30 seconds, right? So there will definitely be a little bit of Julia evangelism in here as well. Hopefully convince some other folks to maybe give it a try at some point. Okay, so without further ado, so I'll first talk about some electrochemical rate modeling. And this is the stuff that Martin just set up really, really well yesterday. But I'll go through it because I think a refresher is nice, and it'll establish the particular notation I'm using, which is not exactly the same as his, although it's fairly similar. Then some fun stuff we did building on some work that he established about a decade ago in constructing these non-equilibrium phase maps as a function of different rate models. And then, like I said, possibly if there's time, a sort of more unrelated bonus story of more recent work from my current group. Great. Okay, so rate modeling. We can start with a sort of typical cartoon that you might see, the energy landscape of some sort of redox reaction. Oftentimes we might be interested in batteries, so I've sort of labeled this as metallic lithium and then lithium plus an electron here, but at this point it could be really whatever your favorite redox reaction is. And so we generally think about there being, at some reference potential, there's some energy state of the, in this case of the metallic lithium, of the reduced species, and then of the oxidized species at some other energy level with some kind of barrier in between. And we can think about activation energies to traverse this barrier in different directions. So if we were going in the reducing direction at this particular reference potential that I've labeled U naught, I just realized I really tried to go through and uniformize notation here, and there might be some U versus eta stuff, but bear with me. So that would be the activation energy to go in the reducing direction. Similarly, if we wanted to go in the oxidative direction, this would be the activation energy that way. We can then think about applying, I guess I use eta for overpotential. Okay, we can apply some overpotential, which will take us to some different potential U. And as Martin nicely showed yesterday, we can think about this as kind of tilting our energy landscape somehow. And so it will, but the crucial thing is that it will couple to the case where we have charge, right? And to first order, at least, we expect the reduced state to stay the same. And now, of course, the activation energies will, in general, be expected to change according to the way that this whole picture sort of tilts. And the Butler-Volmer model essentially is equivalent to saying that these activation energies change linearly with that applied overpotential. And in particular, I'm going to speak more often in terms of rate constants than in terms of currents here, which was sort of the reference case that Martin was using yesterday. But otherwise, I think my notation is more or less the same. He said a lot of details about the details of these prefactors, which go into, of course, the exchange current density. I'm going to mostly ignore those today and just sort of lump them into these prefactors that I'll mostly call A, with superscripts according to which model that we're talking about. And this alpha is the same alpha as yesterday as well. It's the symmetry factor, so you can think about it as sort of like, if this is some generic reaction coordinate, where is the actual peak kind of along that reaction coordinate? And so you have kind of this adjustment for the so-called symmetry factor that comes in like this. Okay, so we can move on to Marcus theory, also beautifully introduced yesterday. And in this picture, we think about the two states instead as residing at the bottom of some sort of parabola about which they're fluctuating, right? And if we do out the math, okay, so then here are now the activation energies within this picture. And when we work through the math, as we learned yesterday, in this case, we end up with these activation energies being quadratically dependent upon the applied overpotential. In particular, it looks like this, where again, we have a prefactor. Lambda is the reorganization energy. Eta is still the applied overpotential. Everything else, I think, is notationally pretty conventional here. And then we can think about, in addition, the so-called Chidsey correction, or the Marcus-Hush-Chidsey model, as kind of an update to Marcus theory that gives us this sort of asymptotic or plateauing behavior rather than the kind of occasionally controversial inverted region that you have in Marcus theory, or the sort of rather unphysical, unbounded predictions that you get from Butler-Volmer. And that arises from basically taking the same expression as we had from the Marcus model on the previous page, but instead you integrate it over the range of electronic energy states against a Fermi-Dirac distribution, or the complement thereof. I guess I've really only specified one direction here, but hopefully folks can kind of generalize. And so this is where I'm going to pause and start interspersing the work that I did. So my PhD focused pretty much entirely on semiconductors. I used a lot of thinking a lot about charge defects and solar cell absorbers and all of these kinds of things. But the point that I really want to make here is I really didn't think about electrochemistry after I passed my graduate thermodynamics class, and really started to learn it much more as a postdoc, and was learning it in the context of batteries and somewhat electrocatalysis. But the work that I'm about to get into that I actually did really grew pretty organically out of just my effort to learn this field and understand the history of these rate models and where they all came from. And when you come from more of sort of a solid state physics background, and I'm sure many folks in the room probably also do, an expression like this looks really weird, right? Because you see suddenly this Fermi-Dirac distribution and there's no density of states that you're integrating against it. And so I asked this question to my postdoc advisor, like, why don't people do this? Aren't you sort of assuming that the density of states is flat here? Surely that would make a difference. And he said, yeah, you should code it up. Like, let's try it out for some things. That would be fun. Later, I found a number of references that showed we were absolutely not the first people to do this. And as we learned yesterday, it went back even further than the references that I found. This paper from Gurney, I think it was 1949, that Martin mentioned yesterday, which was at least probably 30 or 40 years earlier than the earliest reference I found when I later went looking. But here we are. Anyway, the core idea behind MHC, I sort of pithily say here, is like, oh, right, electrons are fermions, and they obey the Fermi-Dirac distribution. And then we can furthermore add in this factor of an electronic density of states to sort of correct for the fact that the DOS may, in fact, not be just a uniform, constant, flat function. In fact, it's usually not. And so I kind of coded this up and was playing around with things. And so if you think about lithium, for example, it's actually, it's wiggly, but certainly, again, and this comes back to another thing Martin touched on, which is that you really can't go to extremely high overpotentials and be confident that you're measuring in a reaction-limited regime. I'm also pretty much entirely neglecting transport and everything else here. We're assuming that we're talking about just a reaction-limited current. And so out to the overpotentials you can get to, and you can basically think of this as sort of roughly sort of how far along the density of states are you kind of scanning by application of your overpotential, right? You don't really see that much variation between the traditional MHC and MHC plus DOS, at least in a sense that you could really make any experimental comparison where you'd convince yourself that it sort of means anything. So this was kind of interesting. We're still a little bit in kind of a pedagogical space here, right? I'm kind of learning for myself, like, okay, I guess I sort of understand why people are able to make this approximation. It actually is, maybe surprisingly fine a lot of the time. And we kind of did this for some other things too. And this is from the paper where, and I'll talk about the code package I wrote to actually do this that we then use for some other things. So we looked at this for different kind of battery components. So here's the one I just showed. Copper is kind of interesting because you've got, of course, that big D band. But again, that's like far enough below the Fermi level that it also doesn't really matter. You can't sort of see a big difference within sort of accessible overpotentials where you would still be reaction limited. You can convince yourself quite clearly that this was our sort of very rough archetype of what an SEI material is. You should not get electrodeposition on the outside of your SEI. That's kind of comforting. Okay, so this is still kind of at this, only a little bit beyond kind of toy models here. But nonetheless, this all sort of makes sense and is checking out. So how was I actually computing all of this stuff? So this is where the Julia evangelism starts a little bit. So I wrote a little package in Julia called electrochemicalkinetics.jl creatively. So we've got a bunch of these standard rate models built in there. It can do some other cool stuff that I'll get to a little bit later in terms of fitting these models to data and things like this. But first I want to show a few other follow-up studies that we did using this package and hopefully convince you that some of the capabilities in there are actually pretty interesting. And so if we go back for a second here and we think about like, okay, what would the density of states have to look like for this to actually matter? I started to get kind of curious about this. And you can convince yourself pretty quickly you need like really large variations very close to the Fermi level, right? And so one example of a material that exhibits this and exhibits it in a somewhat even tunable way is graphene, and particularly these sort of multi-layer twisted graphene materials, right? They have these giant Van Hove singularities, and depending on various things you can do to it, like doping and twist angles, those can end up quite close to the Fermi level. So that's kind of fun. And we started looking at that a little bit. So this was done by some collaborators who just took the code and used it to fit some experimental data on twisted bilayer graphene. You can ask me about the experimental details. I may or may not be able to tell you a tremendous amount, but go and read this paper. It's pretty interesting work. My understanding is this is like actually a sort of tricky set of experiments to do well, and they had to kind of build a custom setup to do it. So it's pretty neat stuff that I probably can't do justice. And then we sort of did an exploratory thing where we took a tight binding model for trilayer graphene, right? I would not want to touch that in DFT with a 10-foot pole. Some of those unit cells get pretty gnarly, but there was a collaborator of ours who developed a tight binding model that they'd sort of validated in a couple of scenarios and worked pretty well. And so here we're looking at, this is just sort of I'm calling it relative DOS peak height. So basically how big are those spikes that we get really close to the Fermi level as a function of the two twist angles, and this black curve overlaid that you can hopefully see is the so-called magic angle curve when you get all this sort of funky, superconducting or whatever, different kinds of weird behavior that people observe. And so in this paper, and I'm not going to talk about every single detail from this, but I think it was kind of fun and interesting. And this was actually led by a really great student named Mohammed Babar. But I was sort of helping on the code side here, kind of explored what would you expect to see in this twisted trilayer system as a function of the relative twist angles, and what kinds of things might you observe sort of modulating electrochemistry via these twist angles was sort of a fun thing to play around with. So that's kind of neat. But where can we go from here? So again, I mentioned there's this other sort of framework that Martin set up. I think it was in a paper 2013, 2014, something like this, of showing, and he started in LFP, so I'll sort of use that as an example, mapping out phase behavior as a function of the current that the intercalation or even deintercalation current that you're running through the electrode, and how you would expect that presumed steady state current to impact the phase stability behavior. And so I'll go through this framework a little bit, and then I'll show you some of what I think are the really cool things that this package I wrote can do with respect to kind of building these phase maps. All right. Okay. So very simple model of the thermodynamics of intercalation, and Martin also covered this really beautifully yesterday. So lithium iron phosphate, increasingly, again, important battery material. It works, so you have this iron phosphate sort of skeleton here, and the lithium ions come in and out as the battery is charging and discharging. So of course, okay, here we now are just looking at the molar Gibbs free energy as a function of the filling fraction of lithium. So this is just a definition. We're going to use a really simple regular solution model, which turns out to work pretty well for LFP. The code has capability to put in whatever sort of model you want. If you like your RK polynomials or whatever else, it's very easy to swap in different models here, but we're rolling with the regular solution model here. And then again, assuming a uniform mixing entropy, which again seems to work pretty well for this material, but you could put in different things here. You could put in different activity models, and we explore that a little bit at the end. So these are the expressions that we're running with here. And probably many folks have seen this in a thermodynamics class, but just as a reminder, this is what the behavior ends up looking like. So the Gibbs free energy as a function of the mole fraction exhibits some different behaviors depending on the temperature. And I've shown a non-dimensional temperature here in terms of that interaction parameter, capital omega. So if you're below the critical temperature, you have sort of this too-well behavior. And then as you raise the temperature, it sort of gets increasingly concave up. Of course, we can think about this also in terms of the, so you have a thermodynamic phase diagram. You can build from this based on when do you get separation into a two-phase region. And of course, this is the critical temperature here, above which you have uniform mixing, and below which you have this two-phase region that becomes wider and wider as you go down. We can also, of course, think about the chemical potential associated with this, which is just going to be the derivative with respect to that mole fraction. Those look like this. So here we've just taken the derivatives of these, and I've shown them at the same 3 reference temperatures. OK, so that's just setting up the framework, reminding some folks of thermodynamics, if it's some of the thermodynamics of these models, if it's been a little while. So how does this connect to the intercalation story? So let's come back to these 3 rate models we were talking about here. What we can do, and this is kind of what Martin initially set up, is, well, let's say that as we're applying this current, what this is really doing is basically changing the chemical potential that's actually experienced by these ions as they intercalate. And we'll add on this term that's related to the overpotential needed to drive a particular current that we specify, and weighted by how many ions there are. OK, so this then we can integrate to get an expression for what the actual molar Gibbs free energy would look like. Pretty straightforward. OK, but if we think about how we actually compute this, we realize that what we've specified in these rate models is I as a function of eta. What we really need is eta as a function of I. This is all well and good if you have Butler-Volmer kinetics with symmetric electron transfer, which is what Martin and his student did, well, this is just a paper by Martin, I guess, in this original paper. But as soon as you have a model that's not analytically invertible, it gets a little bit more gnarly, because for every point on the phase diagram, you need to do some sort of numerical inversion, which is doable, of course, but gets maybe a bit painful. So this is where the Julia part comes in. So now I'm just showing the first quadrant of this to make this picture a little bit easier. Just to make clear what I'm talking about here, we have I of eta. So if we specify some I, we can think about the different overpotentials eta that would be necessary to achieve that current, depending on which rate model we're using. And of course, that might look different. We can, using algorithmic differentiation, which Michael beautifully introduced in the previous talk, access the derivatives of these things, which then lets us, and this, again, is for any model of I at roughly the same cost as computational cost as computing I itself. Of course, as Michael also mentioned, there can be some complications related to memory use and things like that I'm not going to go into in a ton of detail. And what this means is that we can do this inversion with gradient-based optimization, which especially for some of these more complicated models really speeds up the process without having to analytically derive the gradients for all the different variations of, OK, what if I tweak the symmetry, the symmetry parameter, or I want to stick in a different model of activity or anything else. Like, of course, these would all be probably tractable to do out by hand, but it would take a long time. And this just lets it sort of happen automatically and without us having to sort of rederive things every single time. And this, again, is all made possible by the fact that this AD is really, with some caveats, generally a language-wide thing in Julia. AD implementations in a lot of other languages tend to be sort of restricted to sort of domain-specific languages. You can only use a particular subset of functions, et cetera, which often means that if you want to make your code differentiable, you need to basically re-implement things, which is not so much the case here. OK, so phase maps. What do I mean by these non-equilibrium phase maps? So coming back to this expression here, we have, I'll call this a delta mu, and then I showed integrating it as well, and I'm going to call this a delta G that gets added on. And so I'll sort of step through this here. So what I'm showing here, this is a chemical potential in units of that same interaction parameter as before. So the thermodynamic one is shown in the blue dotted line. We've added on a bit that gets us to the kinetic version here. So this delta mu is this vertical distance here. And then as we integrate out to some reference x naught, that gives us the value of that delta g at that point. And then as the inset here, I'm showing this, I happen to be using a Marcus model here. You can also think about the delta mu in these terms here in the context of that rate relationship. When we then translate that to the molar Gibbs free energy plot, it looks like this. So then the delta G, of course, just becomes the vertical distance. And we can do the exact same common tangent construction that we would have done to make the phase diagram previously here. And you can see that where we're going to have that common tangent and where we're going to have phase separation is, of course, going to be different when we have this term added on. And that's kind of the crux of the matter here. And so you get something like this, where you can now make this phase. We got some pushback from reviewers calling it a phase diagram, so we started just using the word phase map because it's not equilibrium. A phase diagram is only an equilibrium, so we've been calling them non-equilibrium phase maps. But as a function of the applied current, and I've here non-dimensionalized the current in terms of that prefactor, so it's basically in units of the exchange current. And we again have this two-phase region where, just to be clear, on the left you'd have the dilute intercalant, on the right you'd have dilute vacancies, and then here there's phase separation. And above some critical current now you actually have just homogeneous mixing. So this is kind of now a fun new little playground we can explore, right? And we can do this along a bunch of different axes. So I'll first show along the top row here we have 3 different rate models. The Butler-Volmer, I'm now making use of the asymptotic approximation also from Martin's group to the MHC model that he mentioned yesterday, and then a Marcus model. So, and I sort of cooked these up so that in this middle temperature, they more or less lined up at small overpotentials. So that's kind of how I tweaked the parameters in this case. Of course, when we go to different temperatures, that's going to shift, but all the prefactors and the reorganization energy where relevant, et cetera, are the same across all of these. So the only things that are changing is the temperature across the columns and then the interaction parameter from the regular solution model in these two here. And so you can see that depending on these different assumptions, these phase maps look quite different, right? Both as a function of the actual parameters and the temperature, and also as a function of which rate model you presume. One thing I want to just remind you of here in terms of sort of a caveat is that, again, we are presuming that this is always reaction limited. So, and I'll note this, I'll come back to when I talk about sort of future work. I think it could be sort of interesting to couple this to a transport model where you could really start to understand the sort of full picture. Because almost certainly at some of the higher currents in some of these cases, assuming that you're actually only ever going to be only reaction limited in a real system is probably a sort of dubious assumption. Okay, so this is kind of a first type of exploration. One other interesting thing that I want to highlight here is, so I've again non-dimensionalized the current in terms of this Marcus prefactor here, and that's actually the same, well, the scaling is different, but the y-axis is current all the way across. And so if you look at where these critical currents show up, if you pick just like 0.1 as kind of a reference scale for these critical currents, I think it's kind of interesting that, you know, at this initial temperature, these differences, and of course this is logarithmically scaled and this isn't, so that's part of it as well, but you know, it's before there's like really dramatic differences, I would say, in the predictions of the different rate models at the level of a Tafel plot. But these phase maps already look quite different. And in fact, in this case, it actually never closes. So it just kind of asymptotes up. So that's kind of neat. We can explore some other kind of dimensions on here. So the next natural thing I wanted to do, because it seemed fun, was we can, of course, make these into 3-dimensional phase maps, right? So now the sort of floor of this space is the traditional thermodynamic TX map. So you can see that kind of classic, regular solution inverted parabola type shape that's sitting on the floor of these plots. But you can see the really dramatically different behavior between, for example, Butler-Volmer and Marcus at different temperatures, and as a function of, as a function of current. And these ones I'm realizing now I forgot to non-dimensionalize, so you can't quite compare to the other one or without. But sorry about that. We can also, and again, this sort of speaks to how nice and easy this is, even when you can't analytically invert things or trivially sort of derive these. We can play with at various asymmetric electron transfer cases. So just as a reminder, that's when you sort of move that peak in the energy landscape back and forth closer to the reduced versus the oxidized state. We can even play with different activity models. So for the vast majority of this, we've been using this center one, but we can play with different models corresponding to things like surface-mediated versus two-site reactions and all these different sort of things. Okay, so that's sort of some of the things, and a bunch of these are explored in this paper from a few years back. So that's kind of fun. I want to talk a little bit about, and I do have some time, I think. I started 10:15, right? Okay, I have plenty of time, great. I want to talk a little bit about some Julia stuff. So I also do some atomistic stuff and DFT and all these kinds of things, as I mentioned. And so I wanted to talk a little bit about Julia stuff and some of the things that actually Michael and I have been involved with together on in terms of atomistic modeling in Julia. So I'll kind of zip through this because it's been mentioned, I think, in 2 different talks now already. But the Julia language, relatively young language, I really designed in many ways for kind of numerical and scientific computing, although has been now used in much broader much broader contexts. I would say one of the original sort of mandates was this notion of solving the 2-language problem, wherein you might prototype something in a high-level and easy-to-use language like Python, but then once you want it to be really performant, you then have to essentially re-implement in a lower level and faster language like C, C++, Fortran. Julia, because it has the capability to be really fast, and I think it's important to emphasize, your out-of-the-box Julia code, I have had cases where it's really fast, and that's fun and satisfying, but that's certainly not all the time. But I still think it's really important that because it's all in the same language, that optimization can now become sort of an iterative process rather than you have to sort of throw everything out and re-implement, because then there's sort of this thresholding moment where you decide when to do that and maybe you just never bother and then it becomes a whole thing, right? So I still think this is a big plus. As has been mentioned a couple times now, there's generally language-wide and quite performant automatic differentiation. Again, this is one where I have had cases where it just works beautifully right out of the box. There are definitely also cases where it does take a little bit of tweaking, either to get it to work in the first place for certain kinds of complicated functions, or to get it to be really performant related to issues of memory use and things like that. And I have much more experience with it in Julia at this point, but I have used some of the tools in the Python-based tools for this, and I really think the fact that there are far fewer restrictions on what kind of code can be differentiable is nonetheless a huge plus of Julia. There's extensive, really, introspection and tools via metaprogramming, which can also aid in things like code programming, benchmarking, optimization, all of these things that at some point in scientific computing you usually run up against. There's increasing hardware portability, so Michael showed this really nicely with the GPU stuff. That's something that a lot of different folks have been working on really hard. There's pretty nice interoperability with other languages in both directions, right? So you can call C, Python, R from Julia. You can call Julia from those languages. Those things, in my experience, do generally work pretty well as long as you don't have like a huge number of like Python dependencies that you want to call from Julia. That can get a little dicey sometimes, but for relatively straightforward things with well-maintained packages, my experience is it really does work quite well in both directions. There's a really active and collaborative online community. This is one of the most fun aspects of it in my experience. I've posted things on the Julia discourse and had one of the like core developers of the language answer my question, which is kind of fun and really makes you feel like you're in it, right? Multiple dispatch is really a core paradigm here. And I'm not going to go into this in a tremendous amount of detail, but the sort of basic idea here is objects don't have methods, functions have methods. So you dispatch a function on some new type. And this was also demonstrated really beautifully in Michael's demo, where he defined this notion of a dual number, which is kind of the core primitive of forward mode automatic differentiation. And all you had to do was tell it how the base functions for essential basic arithmetic operations work on that, and then suddenly everything else just basically works. And I have this quote in here that I stole from Michael, who was also in his talk, and he, I believe, told me he was paraphrasing Alan Edelman, who's one of the original developers of the language, this notion people compose when software composes. And I really think that multiple dispatch in particular, but really to some extent all of the things that I've mentioned here are really key to that composability. And it's just, it just makes the language like more fun and satisfying. Like when I frequently still do need to work in Python for various things, and I just find it so much more frustrating now. Okay, so atomistic simulation, particularly in Julia. So Michael and I are both quite involved in leadership for this Julia MolSim organization, which is kind of the host for a lot of these things. It was started by Christoph Ortner back in 2019. You might be familiar with him if you're in sort of machine learning space. He's been quite involved in these ACE and MACE models that have I think, becoming more and more popular. It is the host on GitHub of DFTK, the package Michael was mentioning, as well as the Molly, which is the Julia-based molecular dynamics code. So it's kind of two real workhorse atomistic simulation codes that are implemented in Julia, both live there. In addition to some interface and utility codes that I'll talk about briefly in a little bit, that Michael and I have both been involved with building up. We've been the convener in real life of a variety of gatherings, including JuliaCon, Birds of a Feather sessions, workshops, mini symposia at the Pathways for Advanced Scientific Computing conference, or PASC, for a couple of summers. And somewhat more recently, within about past year, I guess, we've been running monthly community discussions to just sort of stay up to date on each other's work, as well as coordinate some collaborative development efforts and things like this. So I want to focus on like one of these interface packages in particular. It's probably still the most mature one, and I think it also illustrates something that's kind of a neat feature of Julia that I'll talk about briefly, and that's Atoms Base. So Atoms Base is this interface package, and I'll specify what I mean by that in a second, for specifying atomic geometries. And so you can think about it by analogy to the atomic simulation environment in Python, which if you do any sort of atomistic simulation, you very likely interacted with it, may well be sort of a core part of your workflow. A key idea there is this atoms type that's sort of in common for representing different structures, and then you can sort of attach to it various calculators that represent ways you could compute things, typically energies and forces, about that structure. It allows relatively straightforward combination and sort of mix and match usage of different codes. It's very nice for that. I used it quite a bit in my own PhD. However, it can take a fairly non-trivial amount of development effort to support a new package as a calculator, especially if you really want to achieve good performance. And this, I think, comes fundamentally from the fact that Python doesn't have multiple dispatch in the same way. So you really have to write out a lot of explicit things about how these codes need to talk to each other. And it's absolutely possible to do. There are many great examples of this having been done. But in every case that I know the details of, it really took quite a lot of work. And so the idea is that the way you would do this in Julia is by using the idea of an interface. And so this leverages this multiple dispatch idea quite directly. The notion of an interface is kind of this informal contract. Basically, I give you a list of functions, and I promise you that if you dispatch just these functions, hopefully a relatively limited list, I will just magically allow a bunch of other things to happen for you. I will just make sure that they work. So one of my favorite examples, and I think especially in a more mathematically inclined community, it's a nice example, is an interface for graphs. So specifying graphs as in the mathematical objects with nodes and edges. So there's a set of 10 functions that specify the interface for a graph. Most of these are quite self-explanatory, I think. Get a list of the edges. Give me a Boolean that says whether the graph is directed or not. Tell me how many edges, how many vertices. For a given edge, how many, if it's a directed graph, outward neighbors versus inward neighbors. So relatively simple things that you can understand why they would be the sort of basis for specifying a graph. And then a whole bunch of other things that probably people came across in graph theory or linear algebra or whatever classes these things come up in. Things like centrality measures, computing shortest paths, detecting cycles, traversal algorithms, coloring problems. All of these things are built on top of just these 10 functions. So if you want to define a new graph type, if you dispatch these 10 functions, you can suddenly do all these things on it. And I have a really fun and totally unrelated story about a time that I did this, and feel free to ask me over coffee. I also gave a talk on it at JuliaCon this past summer, very much in the sort of recreational coding category, and I won't go into it here, but feel free to come find me at the coffee break if you want a fun example of this. So Atoms Base is an interface for specifying atomic structures. So and what this gives us flexibility to do is, for example, maybe internally you have different ways you could represent your structure, which is basically, on some level, it's a set of atoms at a set of positions in some box, right? you might, for some reason, probably not performance reasons, want to specify your system as an array of structs. So each atom is some sort of object that's individually specifies, attributes such as position, velocity, mass, etc. In most cases, for performance reasons, you would actually probably prefer a struct of arrays type representation, where you keep lists of all of these things, each list being then of length, the number of atoms in your system. Using this interface, as long as you basically tell Julia how to get the right information out of the structure, Atoms-Base can let you use the same syntax for a whole bunch of things like visualizing these structures, which Michael's built a nice package for, file I/O for various standardized file types, things like featureization for machine learning, and just generally interoperability, right? You can abstract away the details of how the thing underneath is represented, and just sort of do all of the stuff that we want to do to structures. It's currently a dependency of at least 27 registered packages. I haven't updated this in a couple of months, so this might be somewhat out of date, but and I'm not going to read through all of these, but the point is it's for a bunch of different kinds of tasks. So simulation, sort of utilities related to simulations, building and visualizing structures, surrogatization of various sorts for machine learning models, file I/O, etc. And so to showcase this, and I am not as brave as Michael to actually do a live demo in front of all of you, very much kudos for that. I'm going to show you a really, really crappy, but nonetheless functional implementation of AIMD that I did in less than 30 lines of code, thanks to the existence of Atoms-Base. So this is what it looks like. I'm going to zoom in just a second to just hopefully allow you to maybe read some of the code. The top is just package imports, so that's kind of standard stuff. This is just a little utility function for converting to fractional coordinates, which is useful. So I'm going to cut that off and just zoom in here, and maybe you'll actually be able to read some of the text. I recognize it's still kind of small. If you can't read it, no big deal. I'll just sort of take you through the basic structure. So this is for setting up a DFT calculation. A lot of this might look familiar from Michael's demo, and computing a force, and then feeding that force into Molly. So we're using DFTK as a DFT calculator to compute energies and forces, and then Molly to run MD, do some basic setup of DFT. So in this case, I'm just building a little silicon crystal, set up the basics of the MD code, and then run it and visualize it. And I stand by 0% the quantitative meaning of any of this because I set a bunch of really crappy parameters so that I could run it on my laptop. But the point is that it runs, and I built it in basically a couple hours one afternoon. So I think that's pretty cool and a pretty, like, another kind of demonstration of the sort of hackability that Michael was highlighting, right? Which I think is pretty neat. All right, so for this section, I'll give some concluding thoughts and discussion fodder, and I think I will have time at least to go a little bit into the other thing I wanted to. Okay, so I'll talk a little bit about some slightly more recent work at the end. So I would argue that putting in the density of states is a pathway for incorporating more system-specific quantum level information into an interface scale rate model. I showed you some exploration of when and why this might matter. Many times it doesn't. Sometimes it does. It's kind of interesting. I think there's been a lot of fun questions and discussions, and so I thought I'd just sort of put out some things that I've thought about in this vein that might be interesting for discussion, but obviously feel free to ask me about whatever. One thing here is extensions to cases where you might have variations of the density of states along the reaction coordinate, right? So this relates to some of the discussion that Martin brought up yesterday around sort of these inner sphere versus outer sphere reactions and things like this. In addition, and I mentioned this briefly before, coupling to other models to have sort of a more complete description of the system and really understand in various regimes when would you actually sort of observe this as your limiting behavior, and when would you transition to basically being transport limited, I think is interesting, because right now we just kind of look at it and say, well, surely we could never get to that large an overpotential and still be reaction limited, but I don't know. If you stir really fast, I hear, Anyway, I think that the package that I built enables some interesting stuff, including building of these non-equilibrium phase maps, including for rate models that we can't sort of trivially write down an analytical inverse for, and finally, Julia is cool. So actually, maybe I'll pause there for just a moment in case there's some questions on this stuff, because the next thing is relatively distinct, but I'll first go through some acknowledgments. So this work was financially supported by ARPA-E, as well as the Molecular Sciences Software Institute, which is a really great center out of Virginia Tech. My postdoc advisor, Venkat Viswanathan, who was at CMU in the Mechanical Engineering Department, has now relocated to the University of Michigan. Darya Gandhi, who works for Julia Computing, he was really helpful in improving some of the performance of the AD stuff that I mentioned on electrochemical kinetics. So like I mentioned, it really did mostly work out of the box. It was a lot slower when I initially wrote it. And so he was wonderful in helping me understand where that was coming from and reduce things like memory usage and stuff like that. Mohammed Babar, who I mentioned, was the lead on the trilayer graphene study. And then, of course, IPAM for hosting and all the workshop organizers for the kind invitation, and all of you for your attention. So I'll pause there. Then if we can see how questions go. If we run out of questions, I can talk a little bit about the, about the other stuff. Thank you. Yep.